Hi, this is Mira Sarac, a professor at Kadir Has University in Turkey, and I'd like to present my work from my postdoctoral studies at Stanford University. Conventional haptic devices render forces at the fingertip, whether grounded in the world or to the human body. Yet, they cannot be used for applications where the user should have their fingertips free and still take advantage of haptic feedback to learn about the mechanical properties of virtual objects. One solution to such a problem can be relocating the interaction forces from the fingertip to a remote body location like the wrist. The prior work has focused on applying normal or shear feedback to the wrist and showing the potential of this idea rather than investigating the best practices of doing so. We aim at studying the impact of normal and shear feedback on perception. So we designed two haptic bracelets, one in the normal and one in the shear directions. We performed a stiffness discrimination experiment where participants wear the haptic bracelets for the force feedback and the finger sensors for tracking. In the virtual environment, they are given two identical looking objects with different stiffness values. They interact with both objects as needed and choose the stiffer object by dragging it to the designated target. We analyzed the data we collected. The annual results showed that the participants performed significantly better with normal feedback in terms of the discrimination accuracy, but not time spent. Our participants also commented that they felt the normal feedback more intensely than shear, so this may be the reason for the annual results. This comment was probably because we equalized them in terms of the actuator displacements, and after this experiment, we realized maybe we should have done it in a different way. So we needed to study how to create normal and shear feedback with equal intensities. We performed a new experiment where the participants wear the haptic bracelets on both wrists simultaneously. One bracelet delivers the reference stimulus and the participant verbally adjusts the displacement of the other one until both arms feel equally intense. A visual cue shows which arms receive the adjustable and the reference stimuli. Based on the user's responses, a staircase algorithm computes the displacement for the next iteration until their responses converge. We used 3 values for the normal reference and only 1 for the shear. We also integrated a custom force sensors between the end effector of the bracelets and the user's skin to record the interaction forces. After the experiment, we first analyzed the actuator displacements of the converged adjusted stimulus. The results showed that the participants perceived equal intensities when the shear stimulus moved much greater than normal. So, equalizing the displacement creates a perceptual bias towards the normal feedback, just like we observed before. The alternative was to equalize the interaction forces in both directions, but we observed that the normal forces are much greater than shear for every comparison once the participants feel the signals to be equally intense. So, equalizing the forces also creates a perceptual bias now towards the shear feedback. Instead, we propose to model a fit line as a relationship between normal and shear using different reference values in normal direction. Because the fit lines were statistically different for all participants, we should create a personalized model with a calibration before running a perceptual study, which will be our future work. Thank you for listening.